my 1030 class. How are ya? I hope your day's going great. We are going to start today with section 10B, or 10A. 10A is the fundamentals of geometry. So exciting as that is, we are starting the next little section of geometry, which is wonderful. Geometry is great. And we'll be looking at geometrical methods and formulas and ways to come up with areas and volumes and whatnot for the next little bit. All right, until the next test. So these will be the final sections before we take the test on Unit 4. So the word geometry literally means earth measure. And earth measure. So a long time ago, people started inhabiting around the Nile River because the Nile River was a great water source. And then every once in a while, that river would just flood and it would destroy all of the property lines that people had drawn in the sand. And then there were fights, and people were saying, no, this is my property. And somebody by him was saying, no, the line's here. This is actually my property. And a lot of fights broke out. So eventually, they started figuring out geometry in order to measure angles and sides and come up with actual property lines that stuck. And that earth measure is why they call it geometry. Many ancient cultures developed geometrical methods to survey flood basins around agricultural fields and to establish patterns of planetary and star motion. Planetary and star motion is another idea of how what they would use geometry for. They have figured out for a long time now, even before the invention of calculators, what the diameter and the circumference of the Earth is, or how far away the moon is, and the orbits that a lot of the planets actually make. I mean, it's just really awesome what they're able to do. So the Greek mathematician Euclid was the founder of geometry, really. He summarized the Greek knowledge of geometry in a 13-volume textbook called The Elements. And Euclid geometry is a familiar geometry of lines, angles, and planes that we know so well about. I put up a few of his definitions here just because they're just so mind-blowing. Like a point. You see the point here. We know what a point is. Generally, we see it as a location on a coordinate grid. He defined a geometric point as imagined to have zero size. A geometric point is imagined to have zero size. It's a little indirect, abstract for a definition. The geometric line is next here. Again, it is formed by connecting 2 points along the shortest possible path. And it continues in both directions. Line segments are pieces of a line. So if you take a point and a point on a line, the segment is the part between them. And a geometric plane is a perfectly flat surface that has infinite length and width, but no thickness. So you can't say it's 1 millimeter thick. Neither can you say that with a geometric point, that a point is 1/2 a millimeter wide as in circumference or in diameter. It's very, very abstract. So no thickness, just a flat surface, has infinite length and width. That's a plane. So those are some great definitions. Appreciate Euclid for bringing those into the written form so that we can use them. Now, we do talk about dimensions and coordinates. So dimensions of an object can be thought of as the number of independent directions in which you could move if you're on the object. And dimensions, you can think about them by the number of coordinates required to locate a point. So if one coordinate locates a point on a line, 2 coordinates, x and y, locate a point on the plane, and then 3 coordinates locate a point in space. And there is a third axes here that you can go forward or back, like through the board or out in front of the board, as well as up and down and right and left. So those are the 3 spaces. Those are dimensions. So this is 1D, 2D, and 3D. All right. Angles and circles. The intersection of 2 lines or 2 segments form an angle. So you see these 2 lines here. They're segments in this case, but all segments are part of a line anyway. So technically they're lines. This is an angle. And it's where 2 lines intersect. The point of intersection is called the vertex. So you see a vertex right there. And then in these circles, we actually count, if we were to take one segment and an intersection here and another segment and move 1 degree, we call the movement in around circles or encompassing a circle are 1 degree, whereas the entire circle represents 1 3/60th of a circle. So they're 360 degrees if we start here. If you can see my little arrow, and then we move all the way around and then come back to here, that's 360 degrees. All right, and anywhere between them become an angle measure. So if I only move 60 of those degrees, so that would be 1/6 of the circle, then I would have a 60-degree angle. And to measure those angles, we imagine its vertex as the center of the circle. So there's the center. All right. So the degree measure of the angles that subtend or span, I'm going to go through these on my notepad here. So if we're looking at the examples here, find the degree measure of the angles that subtend or span a semicircle, which is half a circle. So if I had 360 degrees, I start here and I subtend half of the circle, I end up right there. Of those 360 degrees, I've gone half of a circle. So what I do is I take 1/2 and times it by the 360 degrees, and I get 180 degrees. So generally, this section of the circle you're subtending, in order to come up with the angle, you're just taking that as a percentage of the entire 360 degrees of the circle and multiplying them to get 1/2 of the circle. As you recall, of means multiply, right? Of means multiply. So 1/4 of a circle. So it'd be 1/4 of means multiply the entire circle, 360 degrees, and that would be 90 degrees. And then 1/8 of a circle, you would take 1/8 and you would multiply that by 360 degrees. And I believe that's 45, but I'm going to check with my handy dandy calculator for sure. So 360 divide 8, and that's 45, just like I thought. Okay. And then E, find the degree measure of an angle that subtends 14/15ths of a circle. Now this one is, I don't know that 15 goes into 360, but I guess I'll find out. But when we take 14/15ths of the circle, that's almost the entire circle, so we better get a pretty big number here. Does 15, let's see, 360 divide 15 evenly? Yes, it does, 24, so that's cool. So that is 24, and then times by 14 is 336 degrees, which is quite a bit. And we thought that to be so because we're subtending majority of the circle by going 14/15ths around it. Okay, next up we have this little angle here. So this is a 60-degree angle. So we're subtending 60 degrees. So we'll just divide that by the whole 360 degrees. And that means that we have gone 6, or I guess you could say 1/6. So we've gone 1/6 of the circle. In that case, you're not going to get a question like that. Majority of them will be like this, but this is going the other way, where we have gone 60 out of 360, which I probably should have done 60 over 360, because that's how much of the circle we've subtended, and it's 1/6 of the circle. So our degrees divide out, and we make it 1/6. All right. Plane geometry is next, and I'm going to go back to the slides for that. Have to be careful to make sure I don't go more than 15 minutes here. I have to stop and then start up a new video in a minute. So plane geometry is the geometry of two-dimensional objects, so in a plane. And one of the things that we look at a lot, in fact, a lot of people say that a majority of our shapes are centered around a circle, but all points on a circle are located the same distance, which is the radius from the circle's center. So here's the center, and if we go out one radius length, then that's going to be our radius. And the diameter is twice its radius. And it passes through the center, must pass through the center, and it would be twice that radius. Now, if we're looking for area and circumference, area of the circle is pi r squared, and the circumference of the circle, we have two different formulas we can use depending on if we have the radius or the diameter, but it's 2 pi r or d pi. Diameter is twice the radius. So you can fill out those little formulas right there. Now, if we're asked to find the area of the circle, we have to use the radius formula. So radius squared times pi. And if we're asked to find the circumference, if we know the radius, we can just take 2 pi r, and if we know the diameter, we can do d pi. So diameter times pi. Now, if we're asked to find the area and the circumference of this circle, then we look and we say, well, what do we have? And it looks like we have the radius, and the radius is 3 inches. So to find the circumference first, because we have the radius, we're going to use the 2 pi r formula. So 2 pi times 3, which is 6 pi. And then you can put that in the calculator. 6 pi would be what we would call the exact circumference. But if we want to be a little more approximate instead of exact and have some actual numbers to deal with, then we would just take 6 pi on our calculator, and your pi is just right there. At least on mine, it's right there. But just look for pi. You don't even have to do times in between. It knows that that's what it means when 6 is placed right next to pi. So that's 18.8. So 18.8, and then we always have to do units because that's a linear in units. So inches is what the circumference is. Now the area is pi times r squared, and that's equal to 9 pi. But on our calculator, if we plug in 9 pi, we get 28.3. Now, because we're measuring these in little units, the cubes, or squares, sorry, square units, we have to make sure that we do inches squared. Or that we're multiplying, it's 3 inches in here, and we're multiplying inches by itself, and everything's squared as well. All right, it looks like we have time for the next one. An oval track is made by erecting semicircles on each of the 70 meter by 140 meter rectangle. Find the length of the track and the area enclosed by the track. So if you slide these two ends together, that's going to be a circle. And that means we have one circle and one rectangular section. So when we're finding lengths in this regard, I'm going to just make sure that we're actually figuring out how long this linear, it's actually curved a little bit, but how long is that right there? That's what we're trying to figure out. So basically, if we throw these two together, squish them together, we need the circumference of this circle with the diameter of 70. So we need this circle with the diameter of 70's circumference, plus we need 2 lengths of 140 meters in order to get this circumference, right? So the circumference here is, we have the diameter, so we'll just do 70 pi, d times pi. We're going to use the d times pi formula, and then we're going to add to it 280 meters. And we can do that on a calculator. So 70, I have to get this, 70 pi, and then plus 280, and that's going to be 499.9 meters. And that's simplified or rounded to 1 decimal place or tenths. All right. The last thing we need to do is the area. And the area is going to be the area of this rectangle, which is 140 by 70 meters, plus the area of the circle with the radius of half of 70, which is 35. And that's going to, if we take those two together, I know this is split in half over here, but half and half, and then the area of the rectangle will have the area of the whole thing. So it's going to be pi, make sure that's clear that that's the radius. Pi, area is pi r squared, so 35 squared plus 70 times 140, because that's the area of a rectangle. So in our handy dandy calculator, we're going to do 35 squared times pi, and then plus 70 times 140, and that is, oh, it's a pretty big area. Is that really so big? It is. And that's going to be square meters because we're measuring that in square meters. So that's 2 meters. All right, I'm going to stop this now and finish the rest in a minute. So hold on, hang tight, and open the next video.